Good day, everyone. I'm Michael Perch. I'm an associate professor at the University of Texas at Austin, and I have a class on subsurface machine learning. And we're going to take a little bit of what could seem like a tangent. We've been dealing with a variety of different types of machine learning methodologies. Just recorded a lecture on naive Bayes classification. Now what we're going to do is talk a little bit about time series analysis. We'll talk about time series data, analysis, models, and I have some hands-on for experiential learning. And let's go ahead and get started. Let's talk about time series data. So it's very common for us to work with time series or temporal information for the purpose of subsurface modeling. Many times we have measurements made over time. Production rates, perhaps so the volumes produced from the subsurface, the composition of the fluids produced from the subsurface. There's many types of things that we work with that are going to be time series information. Now, how do we make comparisons to, say, the spatial data that we're used to working with? And we've been talking mostly about spatial multivariate data sets up until now. Well, first and foremost, when you're dealing with temporal information, of course it's going to be one-dimensional. That'd be cool if it wasn't, but we're generally going to have forward and back in time, future and past. Everything is on a timeline. That makes sense. It's a one-dimensional problem. Observations tend to be clustered, or more commonly, they tend to be exhaustive over the time interval. It's very common to have samples available at regular time intervals in time series analysis. And the prediction problem is most typically a future forecast where we have data available to us up until some date, some time, and then from then on we try to make forecasts into the future. We're trying to build a model that can do that and provide some type of level of uncertainty with regard to that prediction. Now, while I talk about time series data, and I suggest that it's 1D and that it's unique and different than spatial data, I recognize the fact that these methodologies could be employed on one-dimensional spatial information. In fact, it's very natural for us in the subsurface to have data sets such as well logs or even outcrop measured sections, which are fundamentally one-dimensional sets of data that we could apply time series type of analysis to. So there's tons of opportunities to use time series analysis in spatial, one-dimensional, and also temporal settings. How do we visualize or understand time data or temporal data? Pretty straightforward. Line graphs are quite common. Here's an example that I took from online. Population of Ireland, the population of Europe over time up to the year 2000. And you can look at that and see interesting trends or behaviors over time. Stacked area charts are also very common, ones that are proportional and so forth. And also we commonly use other types of novel ways to visualize over time. The steam graph is actually pretty cool, where you get a sense of the rates of downloads of different types of music, and you can see over time how the volumes or relative proportions are changing over time. So there's many ways that we can visualize and understand time series data. So let's talk about a variety of different methodologies by which we can quantify features from time series data. How can we do analysis of it? Now, what's very interesting is that the variogram measure that's very commonly used within spatial problems is also used commonly with time series information. Now remember, the variogram is just defined as a measure of dissimilarity versus distance offset in space. We're going to calculate it as 1/2 the average squared difference of values separated by a lag vector h. And we'll repeat the calculation for different lag vectors, and by doing that, we'll get an experimental function. Now, the precise term for a variogram should be semi-variogram, and it all has to do with this 1/2 term right here. If you remove the 1/2 term, it actually is just a regular variogram. Now, I'm going to be lazy, and you're going to hear me over and over again just say variogram. I never say semi-variogram. Nobody in the profession is using the term semi-variogram. So we'll just assume It's lazy, but we'll assume the variogram is this equation right here. Now, why is the 1/2 there? The 1/2 is there to make all the math work out very nicely. Because of that 1/2 term being tucked in there, this relationship stands. The covariance function over lag vector h is equal to the CIL, or the variance of the problem, the variance of the data set, minus the variogram value at that same lag vector h offset. Now note that the Correlogran is simply going to be related to the covariance function by this relationship right here. It is a standardized covariance function. If the variance of the problem was already equal to 1, you can see immediately that the Correlogran is equal to the covariance function. And why do we love the Correlogran? Because it tells you the level of correlation of data at an offset vector h. Very, very powerful stuff. Okay, so variograms, if you want to calculate a variogram, just to make it completely clear, we could calculate on this data set right here for the single lag, or h equals to whatever distance is between these individual data values. We would just simply compare the square difference of this value, this value, this value, this value, all the way through, get the square difference, sum that up, divide by n to get the average, divide that by 2, we would get the variogram value. Now we could go through and take every one of those pairs and we could plot them, the head value, the tail value, the head value, the tail value. We would get this scatter plot right here, and we would see immediately that if we were to calculate this, that the variogram value is equal to 0.19, because we assume that the data has been standardized to have a variance of 1 before we did the variogram calculation within the calculation program. And you can see the variance is not equal to 1 of this data, of course. But then what we could do is then we could look and say, well, then the correlation coefficient, which we would observe within this plot, is equal to 0.81. And you could calculate that and confirm that the relationship between the correlation coefficient of what we would call a head to tail scatter plot, often known as the H scatter plot, is equal to the CIL of 1 minus the variogram value, a correlation coefficient of 0.81. And then you could go ahead and repeat the calculation, this time do a lag equal to 2 data point offsets. So this to this, this to this, this to this, comparing, jumping over one data point, plot it up. Now you get a correlation coefficient of 0.77. The variogram value is equal to 0.23 in this case, assuming the variable was standardized during the variogram calculation. So not hard at all to do this calculation. In fact, you could go ahead and just take this sheet right here, copy this data set. This data set's available on my GitHub account as 1D porosity. And you could go ahead and perform variogram calculations from that. And if you calculate all the possible lags for this data set, you would get this right here. Now, it might look a little weird. The data set's only 10 meters in length. So once you get to about 5, 6, 7, beyond half the length of the data set, we really are just comparing the edges of the data set with each other, just on the edges, and we're missing all the data in the middle. We don't have enough pairs, so it becomes erratic. It's not very well behaved any longer. And as I mentioned before, the 1/2 term assures us that we can calculate the covariance function as simply the CIL minus the variogram. In other words, the covariance function is the variogram flipped upside down. Now this is super cool because the variogram is a measure of dissimilarity. The covariance function is a measure of similarity, and they're opposite of each other. So the variogram starts with a low value of dissimilarity and becomes more dissimilar. The covariance function starts at a maximal amount of similarity at a distance of 0 equal to the variance of the problem, and then over distance starts to lose similarity, and at some point becomes negatively correlated. Same thing we see when the variogram goes above the CIL, negative correlation. So this is pretty useful. Just for definition now, the covariance function has a different equation. It is equal to the average of the product of the values separated by that lag vector h, and you subtract out the stationary mean squared. Now, of course, covariance function is now assuming you have stationarity. And so that's one thing. Stationarity of the mean is essential for that calculation. Now, We talk about in geostats using the variogram for all kinds of analysis, quantification of spatial continuity, prediction using estimation methods like Kriging, and also simulation methods that try to honor global statistics. But let's put that all aside from now. This is not a geostats class. This is time series analysis for a machine learning class. So let's go ahead and talk about the idea of autocorrelation. Autocorrelation really is equal to the Correlogran. And the Correlogran, once again, is just the covariance function, the measure of similarity over distance h, standardized by the variance of the problem. And therefore, the SIL is going to be equal to 1. We've standardized. We divide it by the variance. So we can calculate this standardized covariance function, or the Correlogran, and we can model it up to a SIL of 1. We can make analysis of it. We're going to use autocorrelation as the term, but really it's equal to the Correlogran. In a geostats class, I would say Correlogran. In an analysis of time series data, I'm going to say autocorrelation. Now, we could define some of the shapes or forms or parts of the variogram for those of you who haven't seen variograms in a while. We have the nugget effect. The nugget effect is an apparent offset at very short distances. The experimental variograms seem to intersect at the 0 variogram value. Instead, there's an apparent offset. The nugget effect is really defined by that offset at distances smaller than the shortest separation distance between data, okay, or pair distance. Then what we have is the variogram experimental values will rise up towards the SIL. Typically, we often see that there may be some cyclicity. And when we reach the SIL, we've reached the point of maximum variance. We define that distance as being the range. The range is the point to which we have some information, some correlation, some type of information. It is also the parameter used to parameterize the positive definite nested structures that we use in variogram modeling. And we're not going to get into that. The SIL is just the variance of the problem, the sample variance. And when we reach the SIL, we no longer have any spatial correlation. Okay, so we've defined the variogram. Now, autocorrelation, if you look at the equation for autocorrelation, there's no surprises. This right here is simply going to be the centered values. See, we've subtracted the mean, so we've centered or detrended the values for all of the properties, product of them over some type of separation distance. Now, because we're working with usually regularly spaced data, we'll say I index, and we'll talk about K being the offset in regularly spaced data. How many data are we jumping to go over? And we're dividing by the variance of the problem. So this is no different than what we talked about before. We have a centered measure of autocorrelation. Now, we should note that, once again, this is just the same as the Correlogran that we discussed before. But what's really cool is we can go ahead and plot autocorrelations for our time series. And when we do that, what we'll typically do is we'll plot the 0, the point at which we have no correlation, and we'll plot some type of confidence interval around that statistic, basically accounting for the number of data that are available to us. And we can use those dotted lines to assess at what point are we significantly different from 0 correlation. In other words, we would reject the null hypothesis that there's no correlation. And that's useful. We can analyze and see the significance of our correlation measure. Now, another method to quantify temporal data is to use the Hurst Exponent. And I like this. It's very compact. It's very simple. It's a single measure that we can use. So it's commonly used within financial markets because the statistic quantifies the long-term memory of the time series. And if you think about that, that'd be a very powerful thing to know for the purpose of making predictions in a financial market. Does this system have long-term memory? Does it tend to do things over time that can be predictable, or does it tend not to? The Hurst Exponent is related to both autocorrelation and fractal dimension. And in order to do the calculations in this demonstration right here, I used a really nice RStats package called Zoo, which was really powerful for getting this done, had great visualizations, really nice tools. Okay, I like R too. I use Python, but I also like R. What is it? It's a power law model. If you look at the equation right here, What we have is R is the range, the max minus the min. S is the standard deviation over N, where N is a cumulative number of samples in the time series. So N 1, 2, 3 different subsets starting at the beginning, and they're cumulative deviations. In other words, we're going to be summing as we go along. You have negative and positive values, and so we're seeing overall how it's going. Now C is going to be a constant, N is going to be the number of samples, and we're going to fit with a power law relationship the Hurst exponent. Okay, and now how do we interpret it? How do we look at it? Well, it's very interesting. I made 4 different time series. The way I did it is I took this initial time series and I used a moving window average on it in order to create different degrees of autocorrelation. When you apply a moving window to a random set of values, it actually does impose autocorrelation. This is actually a method that was used kind of more long ago to make simulated realizations, was to use a convolutional type of method, a moving average window in other words. Okay, so I take that and I get this one that's random. It should be very, very random. This one right here, which is going to start to have some type of relationships. This one's becoming quite smooth. Now the autocorrelation is pretty cool. The way it's visualized is for each interval that you calculate autocorrelation, you'll have like a bar chart, a line chart, and then you'll see the degree of autocorrelation, and then you can compare it to the dotted line, which is showing you the significance level. So we can see significant autocorrelation up to a lag of 7 samples, 0 samples, 12 samples, and 14 samples right there. But then we have the Hurst coefficient of 0.54, 0.69, 0.71, and 0.73. The way you'd interpret it is a Hurst between 0 to 0.5 suggests long-term switching between low and high values. A Hurst between 0.5 and 1 suggests long-term correlation, degrees of similarity over distance. And so this would be very useful in the stock market to know something like that. Now, there's an issue that comes up in time series analysis all the time, and that is stationarity. And what's the definition of stationarity? The metric of interest is invariant under translation. Okay? Stationarity in the mean, variance, and the entire CDF could be posed as stationary in the mean of the feature x, over location vector u, where u bold is the location vector, is equal to a constant mean that would be the same everywhere. Stationary variance, the variance over locations u for all possible u locations within the area of interest, are just equal to a constant variance, and the entire CDF, capital F is the CDF x of the feature x, dependent on location is just constant everywhere. Okay, so that's how we would define stationarity, and that's important. What about stationarity in time series? Well, how do we detect stationarity? Well, there always is ocular inspection. Sorry, but it is a good idea. Use your eyes, look at the data, see what's happening. Now, clearly this is a data set that has a lot of cyclicity that seems pretty consistent, but there is this constant rise in the values. And so we'd say that doesn't look very stationary, but of course it would depend on the scale of the observations. We might suggest that this data set now looks somewhat stationary. But if I was to zoom in and consider just one cycle, now it once again looks very non-stationary. So furthermore, on detecting non-stationarity, a very nice idea is to do some type of local statistical calculation, moving windows, time rolling statistics. So what we can do is we take the original data set we have, and its production over time. It has some cyclicity going on with regard to its production and some increasing trend. And what you can do is you could calculate over some rolling window, in this case 20-day production, uniform weighted window. I can calculate the mean, the P2.5, the P97.5, the 97% confidence interval on the statistic over the 20-day window. And I can go ahead and calculate that, and I get this. The red line is the rolling mean. The gray lines are the upper and lower bounds of my confidence interval. And we can assess whether or not we have non-stationarity based on that rolling window. Now, of course, it's going to be sensitive to the duration or interval that we use on that rolling window. If you were to use a very large window, larger than these individual cycles, you would start to smooth out those cycles. but you would still see that rising trend within the data set, and we'd assess that it's non-stationary. How do we go beyond ocular inspection and rolling statistics to check for non-stationarity? You can detect it with a hypothesis test. There's the Dickey-Fuller hypothesis test for whether or not you have a constant mean with a phenomenon. And so the null hypothesis is the time series is non-stationary. Interesting, eh? The alternative hypothesis is the time series is stationary. And so we can apply a test at a specific alpha level, and we can see if the p-value is less than alpha, then we reject the null hypothesis and we adopt the alternative hypothesis that the time series is stationary. And so let's do a test. This was done within RStats, and a really nice example of taking a data set that has this really climbing and cycling, and we go ahead and we calculate and we see, oops, we will go ahead and accept the null hypothesis that the time series is non-stationary. And then this example right here, actually in order to get to that sample, all I did was a first difference on the production from this data set right here. I'm about to talk about how we do differencing with time series. And when we went ahead, and differencing is really a method to try to make the data set stationary. So let's go ahead and we do that. And when we calculate, we reject the null hypothesis and we now have adopted the alternative hypothesis that the time series is stationary. Now, how do you deal with non-stationarity? For inference or prediction, we must deal with the non-stationarity. We may see that it's something we can predict over the long range, and it includes important information. We don't want it to be left to some type of statistical model. Maybe we can remove it, model it deterministically, and improve the prediction of our problem. This is commonly done in geostatistics with spatial phenomenon. In fact, probably 90-something% of the models I ever built or reviewed in the subsurface had some type of non-stationary deterministic component mixed into it, and a model statistically based on the residual from that deterministic model. So there's a variety of ways we could build trends. A common way to do it is to use a moving window average to do that. And so we could take a 20-day, 40-day, 100-day moving window average and apply it to the data set, and then we could go ahead and remove and look at the residuals from that. Now, when we do that, this is what it looks like. So in the first case, we had the only 20-day moving window, so it doesn't look very, it's still quite a bit of detail in that trend. And when we go ahead and remove and work the residuals, we still have these little cycles. They have very low magnitude, and that would be detrended. It's simply taking the black line at every time, the original data, and subtracting the red line, which is the rolling mean 20-day trend model, and we get a residual to work with, and that's the residual right there, the 20-day residual. This is the 40-day model right here. When we go ahead and calculate the residual, you see they're much higher magnitudes now. We can see the higher magnitude type of cycles are being represented, and the 100-day rolling mean, you now see that we have quite a bit of variability now captured in the residual. There's much less variability in the trend model. We'll talk about variance additivity between the trend and the residual shortly. So what's the whole idea of this geostatistical concept of trend modeling with residual? It all comes down to this. If I'm trying to make a prediction in this space, and this is distance in the x direction, I have samples at 1, 2, 3, 4, and 5 locations, and this is V shale. It's a fraction of shale within the samples. It's a one-dimensional data set. When we look at it and we're trying to make a prediction at this unsampled location right here, it's probably really important to observe that the data seems to be monotonically increasing, maybe with some noise or something. And so we could go ahead and fit a trend model to that. Maybe a very simple linear trend is shown right there. And if we fit that trend, now what we can do is we can detrend the data. We're now working with a residual. Trend has been removed. Let me go back and forth from there to there. Notice we now have negative and positive values. We have a residual. Everything looks like it has a much more stationary mean now. We can go ahead and fit a model. The solid line right here is the model. We're honoring the data at the data locations. Away from the data locations where we're outside of range of correlation or autocorrelation, we can go ahead and say we'll estimate with the trend value the zero residual value. And that's pretty useful. And then what do we do when we're done? We have to restore back to the original V-shell. This is the trend and residual workflow. Got to go back to original V-shell. Can't put negative V-shells into any type of model. Have to be back in the regular units of the property. Now, why do we want to do the trend removal, model the residual, add the trend back in type of workflow for modeling? Because if we don't, this is what we would get. If we tried to build the model in the regular space without removing the trend first in the regular V-shell, we would be assuming some global mean for V-shell away from correlation. At the range of correlation away from any of these training data or data samples, we're going to estimate with the global mean. That will cause a systematic overestimation in the low location and a systematic underestimation in the higher value locations on this side of the model. But if we build the trend first, remove it, work with the residual, we get a much more reliable estimation between the data because we're relying on the trend, not a global stationary mean. Well, now what's interesting is with trend modeling, we must identify and model the trends. Now, what's very interesting is that the determination of what is trend or not will depend on the scale that you're looking, the scale of the data, and the scale that's required for building the model. And so in this case right here, maybe this looks like a trend. This was from the book with Deutsch. Or maybe what we'll have is we zoom in and we'll start wanting to model the features, these finer scale features too. Now, data-driven trend modeling is a little bit dangerous. It's not just take the data and try to contour it up or something. We should be including all possible sources of information and expert knowledge in geology, geophysics, petrophysics, reservoir engineering, and so forth. The trend is a very important decision. There's a very important concept related to trend modeling, and that's the additivity of variance. In fact, the total variability of our feature is equal to the variance captured by the trend plus the variance in the residual that remains, plus 2 times the covariance between the trend and the residual. Now, if the trend and residual are independent of each other, that symbol indicates independence, then that covariance between the two should be 0. In that case, we can say that the variance of the residual is equal to the variance of the problem minus the variance put into the trend. In other words, we can represent the variability as being the total variability is this pie chart and 2 components. Variability assigned to a known trend, deterministic model. Variability assigned to the unknown residual, that's a statistical model. So this is a really powerful concept that as we build a trend model, we're balancing between known and unknown components. We're directly impacting the overall uncertainty of our model. And so we got to make sure that we understand that. Now, in case you're sitting here going, wow, additivity of variance, that seems unusual. That doesn't seem like that works. On this slide right here, we show the concept just taking the fundamental equation in expectation for a variance, the expected value of the squares of the values, the samples, minus the square of the expectation, and simply saying what would happen if I said replaced z feature with x plus z. The trend is additive with the residual, so it's just trend and residual. And if you go ahead and work this out, you'll find that the whole thing will simplify down to the variance of the x, the trend, the variance of the y, the residual, plus 2 times the covariance between the two. All right, so this is really cool. Additivity of variance works, and so we're going to want to build trend models even with the purpose of time series analysis and trends within time. Now, let me just define, when we talk about trend models, we're talking about a deterministic model. And so when we have a deterministic model, we'll define it as a model that assumes perfect knowledge without uncertainty. It's based on knowledge of the phenomenon or trend fitting from the data. And as I said before, most subsurface models or spatial temporal models, as we see now, will have a deterministic component, the known, and a stochastic statistical component, which is that residual, and treated as unknown. Okay, time series analysis. What about time series differencing? This is a very powerful methodology because what we'll find is the fact that we need to work with stationary time series. Now, what I showed before was more of a geostatistical trend fit, moving window, and so forth. What often happens in time series analysis is we apply a set of differencing. It's a method to remove non-stationarity. The differencing calculation goes like this. The first order difference, y1, is equal to taking the original value at I plus 1 and subtracting the previous value in the time series. You see, that's why we call it differencing. You just go along and you replace the value at the current location with the value that was there minus the previous value. And so by going through, we can create a brand new feature which is just going to be equal to the value at that location minus the previous value at the location before. Now, difference may be applied multiple times until the result is stationary. And so you'd have first order differencing, just going through and calculating the difference between the current value and the value before. Just keep going, keep going. Now note that's not cumulative. That's why we show a z and a y variable. So we're going to just go through the data set and just get the differences. We're not doing anything cumulative with this. Okay. Differencing may be applied multiple times until the result is stationary. Second order differencing would be you just simply take that first difference and do it again, and do it again, do it again. And so what does that look like when we do differencing? This is our original data set right here. Here's the first difference, and look at it. It's already become quite a bit more stationary. And look at the second difference. Now, if you calculate the autocorrelation, you can see the strong impact on autocorrelation. We had very long-range cyclic autocorrelation, as you'd expect looking at that original data set. After the first difference, check that out. Much of the autocorrelation has been removed. Over much of the lag distances, you're within the confidence interval for being zero autocorrelation. And by the time you get to the second differencing, there's really no longer any autocorrelation at all. It's just really zero across the entire length scale, or lag offsets. So, time series decomposition. Now, this is an interesting idea. We've already talked about quantification through Hurst coefficients, autocorrelation, and we've talked a lot about stationarity and removing stationarity for our analysis. There's methods to actually decompose a time series into multiple additive components. Many time series have common components such as a trend, a mid to long range autocorrelation structure like shown here, where we have constant, kind of a monotonic increase at the large scale. Seasonality, some type of regular cycles. So if you look here, we have kind of a repeating seasonality here. And then noise. If you look in addition to that, you have some wiggles on top of everything. That's the remainder after we remove all of the above. The trend, the seasonality, and the noise is the remainder. Okay, so Python stats model has functions to automatically decompose a time series into a model of trend, seasonality, and residual. So it took this time series right here. It gave me this trend component right here. It had detected this seasonality, which if you ask me, it seems to me it's capturing noise as seasonality at that point and it's providing a residual. Now, I'm not super happy with that result, the automatic detection result. I would rather probably have something where I use a little bit more of my judgment to support that model. Okay, what I'll do now is I'm going to break up this lecture and I'll talk specifically about a type of time series model that uses seasonality, trend, and residual to make predictions, but I'll do that in another lecture. I think I've been talking too long in this lecture. I hope that this was useful to you, talking about time series analysis. I'm Michael Perch. I'm an associate professor at the University of Texas at Austin. I'm the Geostats guy on Twitter and YouTube and GitHub, where I share a lot of resources. I share every single one of my lectures. Why do I do that? Well, because I think as a professor, I should make education as open as possible, and I should share everything I have with whoever in public or society who wants to learn. And I'm very much into outreach, and who knows, maybe there's some young high school students watching this and they're going to decide to become an engineer. Wouldn't that be a wonderful thing? I never regret becoming an engineer. So, or a geoscientist, or any type of scientist, or anything in STEM would be awesome, or anything that you want to do. So anyway, I hope this was helpful to you, and take care.